In the dark and desolate night sky of the 1970s, astronomers encountered a surprising truth. Our Milky Way galaxy was not stationary. Under the influence of invisible forces, it was drifting toward an unknown destination. Of course, together with our galaxy, we were drifting as well. This discovery was the beginning of the story of the Great Attractor, which would radically change our understanding of the universe. Astronomers Arondant Tully and Richard Fisher, while observing distant galaxies with the Parkes Radio Telescope in Australia, noticed that all neighboring galaxies were moving in a common direction. Why were all these galaxies moving the same way? And what was behind this massive cosmic flow? Seeking an answer to this question was one of the greatest mysteries before astronomers. So, what secrets would this mystery unlock for us? If you are ready, let's begin. At the same time, scientists working on the cosmic microwave background radiation, also known as the CMB, also encountered similar clues. The temperature variations observed in this radiation, a relic from the early universe, could not be explained solely by the galactic motion of the sun. No matter how hard scientists tried, they could not figure out what our galaxy and the other galaxies were being pulled toward. Have you ever thought about it? While you are sitting right now, you are actually traveling through space at hundreds of kilometers per hour. Faced with this reality, the human mind almost freezes. The greatest problem of this mysterious source of attraction was that it could not be seen. This cosmic region, called the zone of avoidance, was covered with dense clouds of dust and gas at the center of the Milky Way. What kinds of mysteries were being hidden within these gas and dust clouds away from outside eyes? It was as if the universe was hiding its greatest secret from us. Why does the zone of avoidance form? The galactic disk of the Milky Way, when viewed from our position, covers about 20% of the sky. The stellar gas clouds and cosmic dust particles in this region absorb visible light, making the objects behind them invisible. Perhaps seeing beyond this curtain of mist would solve the mystery. So, how did scientists overcome this problem? This is where the power of technology came into play. Since radio waves, infrared rays, and X-rays can pass through dust clouds more easily, astronomers began to use these wavelengths to look beyond the zone of avoidance. To understand this situation, let's make an analogy. Imagine being adrift on a small raft in a dark ocean on a moonless night. You don't know where you're going, you only feel that a strong current is carrying you toward an unknown destination. This was exactly the situation astronomers were in during the 1970s. Brent Tully and Richard Fisher developed an important cosmological tool known as the Tully-Fisher relation. This relation revealed the connection between the rotation speed of a spiral galaxy and its brightness. And this allowed us to calculate the rotation speeds of galaxies, indeed even groups of galaxies, much more easily. Now we had a compass. The duo measured the Doppler shift of hydrogen gas in galaxies using 21-centimeter radio wave observations, calculating the velocities of thousands of galaxies. These measurements were not just numbers, they carried the key to one of the greatest mysteries of the universe. Large observational projects, such as the 2D Galaxy Redshift Survey and the later Sloan Digital Sky Survey, expanded upon the work pioneered by Tully and Fisher. Thanks to these projects, the cosmic motions of hundreds of thousands of galaxies were mapped. This cosmic force, which could not be understood for decades, finally received a name: the Great Attractor. This name was in fact an expression of the scientists' helplessness. It was enormous, yet we could not truly figure out what it was. Unseen, unmapped, incomprehensible, but with an undeniable influence. The Great Attractor had drawn not only the Milky Way,
but also thousands of neighboring galaxies into its grasp. These galaxies, home to billions of stars and countless planets, were being pulled toward this mysterious point, like moths drawn to a flame. How great is the influence of the Great Attractor? This force affects all the galaxies within the region known as the local supercluster, which has a diameter of about 100 to 200 million light-years. In this region, thousands of galaxies are found, and all of them are in a flow toward this mysterious point. In the 1980s, observations made with IRAS, infrared satellite astronomy, began to see the structures behind the zone of avoidance. This satellite, working in infrared wavelengths, was able to pass through dust clouds and helped determine the position of the Great Attractor more precisely. Cosmic microwave background observations provided one of the strongest pieces of evidence for the existence of the Great Attractor. Measurements made with the COBE satellite showed that the CMB was about 0.0035 Kelvin warmer in the direction of the constellation Leo. Why is this temperature difference so important? Since the CMB is the light emitted when the universe was 380,000 years old, it is almost perfectly homogeneous. Over time, it has formed an almost perfect mixture within itself. The small differences within this homogeneity carry the traces of our cosmic motions. The Planck satellite and later observations measured this dipole anisotropy even more precisely, determining that the Milky Way is moving at a speed of 627 plus or minus 22 kilometers per second relative to the cosmological reference frame. With the advancement of technology, radio, infrared, and X-ray observations began to look behind the zone of avoidance. What we learned from these observations was surprising. At the center of the Great Attractor was a gigantic galaxy cluster called the Norma cluster. Located about 220 million light-years away, this cluster was several times larger than a normal galaxy cluster. But the story did not end there. The discovery that truly shocked us was only just beginning.
The 2-mass, 2-micron all-sky survey project mapped the galaxy distribution behind the zone of avoidance with infrared observations. These studies confirmed that the Norma cluster was indeed the largest mass concentration in the region. The galaxy cluster called Abell 3627 is the densest part of the Norma cluster. This cluster contains at least 1,000 galaxies and has a total mass of around 10 to the 15th solar masses. It is truly difficult for us to comprehend and grasp such enormous amounts. X-ray telescopes such as the Chandra X-ray Observatory and XMM Newton observed the hot gas clouds in the Great Attractor region, providing important clues about the mass distribution of this gigantic structure. The Great Attractor is not just the Norma cluster. Modern research shows that this name actually represents only the visible part of a much larger cosmic structure. With the discovery of Laniaka's supercluster, it became clear that the Great Attractor is the gravitational center of this enormous structure. The dimensions of Laniaka are truly breathtaking, a structure 500 million light-years in diameter, containing 100,000 galaxies and weighing 10 to the 17th solar masses. Can you imagine such a massive body? Compared to us, we are no different than a speck of dust. This discovery showed that the Great Attractor was not just a local phenomenon, but part of one of the largest structures in the universe. Modern cosmology shows us that the universe is not a static place at all. Everything is in constant motion. Planets orbit stars, stars rotate in galaxies, galaxies pull each other. This cosmic dance has been going on for billions of years and will continue in the future. And of course, we too will join this cosmic dance along with them. So, do you feel that you are part of this cosmic dance? Most people forget this fact in their daily lives, but in reality, we are all passengers on this magnificent cosmic journey. Our motion toward the Great Attractor happens at a speed of about 100 kilometers per second. The speed may sound like a lot, but when considered on cosmic scales, the Norma cluster is so far away that reaching it would take more than 100 billion years. So unfortunately, it is impossible for us to physically get there. But maybe one day, our technology could take us there. These enormous distances and timescales reveal how vast the universe truly is. The human mind struggles to grasp these dimensions, but thanks to modern science, we can understand these cosmic realities. Thanks to the James Webb Space Telescope and other modern observation tools, we are learning more about the Great Attractor. These observations help us understand not only the present state, but also the past and future motions of galaxies. Mathematical tools, such as the Monge-Kentrovich equations, allow cosmologists to model these cosmic motions. So mathematics is truly a universal language. Not only on Earth, but also in space, it works beautifully, bringing mysteries into a dimension we can comprehend. The discovery of the Great Attractor is not only an astronomical achievement, but also an important step in humanity's journey of understanding its place in the universe. This discovery shows us that the universe is a dynamic place. Nothing is static. Even though cosmic forces do not affect our daily lives, they shape our existence. Thanks to scientific curiosity and technology, we can understand invisible forces. Research on the Great Attractor is still ongoing. Each new discovery illuminates this cosmic mystery a little more while also bringing new questions. For example, what other cosmic structures lie beyond the Great Attractor? How will these structures affect the fate of the universe in the future? Do you wonder about the answers to these questions? Modern cosmology is revealing new faces of this mysterious universe every day. Scientists from different countries of the world are coming together to solve the secrets behind these mysteries, working with great care on the greatest enigmas of the universe. The discovery of the Great Attractor shows how complex and fascinating the universe is. The scientific adventure that began in the 1970s is still ongoing today and will continue in the future, full of new discoveries. In-body simulations carried out with modern supercomputers show how structures like the Great Attractor form and evolve. These simulations, by modeling the interaction of billions of particles, provide predictions about the past and the future of the universe. New generation observational tools, such as the Euclid Space Telescope and the Vera Rubin Observatory, will provide much more information about the nature of the Great Attractor in the coming years. As a part of this cosmic journey, you are taking part in the great adventure of the Milky Way. And this is such a magnificent thing. It reminds us again and again how small we are in the universe. The problems that seem gigantic to us are nothing more than specks of dust, while the universe surrounds us in all its majesty and makes us even more free. With every breath you take, you are getting a little closer to the Great Attractor, though of course toward a target 100 billion years away. How does this cosmic dance make you feel? Maybe tonight, while looking at the sky, you can take a moment to feel this immense motion of the universe. After all, you too are part of this great cosmic flow. Can we ever truly be motionless? This question is one of the fundamental questions that has occupied philosophers and physicists for centuries. But modern cosmology offers us a surprising truth. In the universe, there is no such thing as absolute motionlessness. Everything is in constant cosmic motion, including you. Thanks to the forces of gravity, every object in the universe has been in continuous motion since the Big Bang. For thousands of years, the brightest scientific minds in Europe and the Middle East believed that the Earth was perfectly still and that the heavens revolved around it. This is rather ironic because everything we thought turned out to be the complete opposite. This geocentric model was mathematically quite a complex structure. Ptolemy's model proposed that while planets traced small circles called epicycles, the centers of these circles revolved on larger circles called deferents.
This complicated system required more than 80 circles to explain observations. In 1543, Nicholas Copernicus published his work De Revolutionibus Orbium Celestium on his deathbed. This radical study placed the sun at the center of the universe and showed the Earth in motion. For that time, this was great courage because it was the first time such an idea, so different from all prevailing beliefs, was expressed. If the Earth is moving, why don't we feel it? This question was one of the strongest objections to Copernicus's theory. People could feel the wind when running and see their targets grow larger as they approached. So why were there no similar effects for the Earth's motion? Isaac Newton's theory of gravity solved this paradox. According to Newton, an object moving in empty space cannot be felt by an observer moving along with it. Since there is nothing in a vacuum to push against, our motion cannot be detected. But there was something Newton had not taken into account. This theory was only valid if the speeds were the same. If the observer moved at 100 kilometers and the observed object at 150 kilometers, then of course the difference of 50 kilometers would be noticed. Newton's concept of absolute space made an important assumption, that the universe had a fixed reference frame and all motion could be measured against it. This idea dominated the world of physics for more than 200 years. In 1905, Albert Einstein demolished Newton's idea of absolute space with the theory of special relativity. According to Einstein, all inertial motion was relative. This idea, which bulldozed through all previous knowledge about space, shook the entire world. The fundamental principle of the theory of relativity is this: two observers moving at constant speed have equal rights to claim which one is in motion. Imagine traveling in a powerless rocket ship in space. Your friend coming toward you may say that you are standing still, while you may say that he is standing still. Both perspectives are equally valid.
So, what are the practical consequences of this theory? The theory of relativity is not just a philosophical concept. It affects our daily lives, from GPS satellites to atomic clocks. Although Einstein defended relativity, the universe offers us a special reference frame: the universe itself. The universe is not static. It is a constantly growing and dynamic system with the expansion of the universe. This expansion creates a preferred coordinate system for cosmic motion. So, exactly how much will the universe continue to expand? With Edwin Hubble's discovery in 1929, we learned that distant galaxies are receding from us, and the farther they are, the faster they move. This Hubble's law was definitive proof that the universe is expanding and formed the foundation of cosmology. How does this expansion create a reference? Every motion that deviates from the general flow of the universe's expansion is called peculiar velocity. These velocities range from a few hundred to a few thousand kilometers per second and form the basis of cosmic motion. Even while you are reading this right now, you are moving at tremendous speeds. Let's examine this motion layer by layer. If you live on the equator, you are rotating at 1,670 kilometers per hour. For most people living in mid-latitudes, this speed is about 1,000 kilometers per hour. Can your mind grasp this speed? During an 80-year human lifetime, you would travel nearly 1 billion kilometers just because of Earth's rotation. This distance is greater than the distance from the Sun to Jupiter. Can you believe it? The Earth orbits the Sun at an average speed of 30 kilometers per second. This means 30 kilometers every second,
100 times faster than a jet plane. During your lifetime, you would travel about 80 billion kilometers because of this motion. What do these numbers mean? Since Earth's orbit is approximately circular, we are not actually going anywhere net, but it is still an incredible amount of motion.
Why is this speed so important? In fact, this number is one of the strongest pieces of evidence for the existence of dark matter. The total mass of visible matter in the Milky Way is not enough to keep the Sun in orbit. So then, how can the Sun stay in place? Is there a mysterious force holding it? Without dark matter, the Sun's current speed would have flung it out of the galaxy billions of years ago. But the Sun is still here, bound to the galaxy by the gravitational effect of invisible dark matter. This is one of the greatest mysteries in the field of cosmology. The Sun does not just orbit, it also performs a wave-like motion above and below the galactic plane. Like a buoy floating in a dark ocean, it rises thousands of light years over millions of years, then passes through the galactic plane and descends the same distance. Currently, the solar system is passing through a special region called the local bubble. This bubble is a cavity in the interstellar medium created millions of years ago by a supernova explosion. The density of this region is only 1/10 of the Milky Way's average. That means we may be the heaviest mass in that void. Galactic motion does not end here. The Milky Way also exhibits special cosmic motions relative to the universe's expansion. The most dramatic movement is the approach toward the Andromeda galaxy, the Andromeda-Milky Way collision. This galaxy collision, which will occur in 4 to 5 billion years, will actually be a slow merging process. The future of the Milky Way will be shaped by this cosmic event. The two galaxies will dance around each other for hundreds of millions of years, eventually forming a single giant elliptical galaxy. What happens during this galaxy collision process? Most stars do not collide, but their orbits change dramatically. Gas clouds collide, causing intense bursts of star formation. This will be one of the greatest events in the history of cosmology. In the 21st century, motion measurement has reached incredible precision. The Gaia Space Telescope measures the positions and velocities of billions of stars with micro-arc-second accuracy. How precise is this? Micro-arc-second accuracy is like seeing a coin on the moon from Earth. Achieving this level of precision as humanity is truly very promising. Pulsar timing has also revolutionized motion measurement. Pulsars are rotating neutron stars that emit signals with the precision of 1/1000th of a second. Changes in these signals can reveal even the tiniest movements in space. Even at the atomic level, there is no absolute stillness. The Heisenberg uncertainty principle states that we cannot know both the position and momentum of a particle exactly at the same time. Even at absolute zero temperature, minus 273.15 degrees Celsius, atoms move due to zero-point energy. Quantum fluctuations show that even the vacuum is in constant activity. Dark matter is the unseen regulator of cosmic motions in the universe. From the rotation curves of galaxies to galaxy clusters, the gravitational effect of dark matter shapes all large-scale cosmic motions. Just as it affects us, it affects the entire universe. What would happen without dark matter? Galaxies would disperse, galaxy clusters could not form, and the universe's present structure would never have existed. Cosmic motion and dark matter are indispensable partners in the architecture of the universe. This also makes the formation of massive structures like the Great Attractor and the Laniakea supercluster possible. Dark energy also has a major impact on cosmic motion. This mysterious force, which accelerates the expansion of the universe, constantly increases the distances between galaxy clusters. It is as if a pushing force is slowly opening up the gaps between them. Nothing in the universe stands still. From the tiniest quantum particles to the largest galaxy superclusters, everything is in constant cosmic motion. This cosmic dance has been going on for billions of years since the Big Bang and will continue for trillions of years until the end of the universe. Modern cosmology shows us that thanks to dark energy and the cosmological constant, the expansion of the universe is accelerating. This will make cosmic motions between galaxy clusters even more dramatic in the future. As you read this text, at the same time, you are rotating with the Earth at a speed of 1,000 kilometers per hour. You are orbiting the Sun at a speed of 30 kilometers per second. You are revolving around the galactic center at a speed of 230 kilometers per second. You are moving toward the Great Attractor at a speed of hundreds of kilometers per second. How do these immense cosmic motions make you feel? Perhaps this cosmological perspective can help you see the small problems in your daily life from a different angle. Considering the future of the Milky Way and the Andromeda collision, we are all traveling together in this great cosmic dance. But is that all? Of course not. There are far more fascinating theories, and we will explore them together now.
As you read these lines, right now, you are on an immense journey that you do not even notice. In fact, even while watching this video, you are moving at a speed of kilometers per second. Fortunately, we do not feel this. The Earth's rotation around its own axis spins you at a speed of 1,600 kilometers per hour, depending on the latitude you live in. If you live at the poles, your rotational speed is close to zero. However, for most people living in mid-latitudes, our cosmic motion experience is around 1,000 kilometers per hour. This incredible speed makes the distance we travel in a human lifetime astonishing. During an average lifespan of 80 years, we cover approximately 1 billion kilometers just due to the Earth's rotation. To simplify it further for you, this 1 billion kilometers is roughly equivalent to traveling to the Sun and back 3 times from Earth. How is that? Impressive, isn't it? But from a cosmology perspective, this is just the beginning. The Earth's orbit around the Sun represents a much larger cosmic motion than its daily rotation. We orbit the Sun at an average speed of 30 kilometers per second. This speed is so great that during a lifetime, this orbital motion takes us approximately 80 billion kilometers. Of course, since this motion is circular, we do not actually get anywhere, we only trace a huge spiral. But we are not the only ones moving. The entire solar system itself is moving as a complete system. Here is where the expansion of the universe and the relationships between galaxy clusters come into play. The solar system orbits the galactic center in direct connection with the future of the Milky Way. This orbit lasts 230 million years and has been completed only 20 times since the Big Bang. That means not even one full galactic year has passed since the extinction of the dinosaurs. What an extraordinary timescale! The Sun's motion around the galactic center opened the door to one of the most important discoveries in the history of cosmology. When astronomers calculated the mass of visible matter in the galaxy, they encountered a surprising result. The Sun's current speed was much higher than what the visible mass of the galaxy could account for. At this speed, the Sun should have been ejected from the galaxy billions of years ago. However, the Sun is still here, still in orbit. This indicates the presence of much more mass in the galaxy than is visible, dark matter. We have not yet fully discovered what dark matter is, but the frightening part is that about 85% of our galaxy is composed of this dark matter. This is eerie because we do not know exactly what it is, yet it is everywhere. This dark matter can be compared to invisible glue that holds the galaxy together. Through the effect of gravity, dark matter keeps the solar system and billions of stars bound within the galaxy. Modern cosmological studies show that galaxies consist of approximately 23% dark matter and 73% dark energy. The Sun does not only orbit the galactic center, it also performs wave-like motion above and below the galactic plane, similar to waves in water. This motion occurs in cycles lasting millions of years. The Sun rises thousands of light years above the galactic plane, then descends back to the plane, completing the cycle.
Currently, the Sun is located in a region called the local bubble. This bubble is a void created millions of years ago by a supernova explosion, with a density about 1/10 that of the interstellar medium in galaxy clusters. We know that under Earth conditions, this void would be considered a near-perfect vacuum. The solar system entered this bubble 5 to 10 million years ago, and crossing its thousands of light years width will take millions more years. This cosmic motion also affects life on Earth. During the Sun's passage through the galactic plane, increases in cosmic radiation may occur, which can influence evolutionary processes. The future of the Milky Way is shaped not only by its internal dynamics, but also by external influences. Our galaxy exhibits its own motion against the backdrop of the universe's expansion. Measurements of the cosmic microwave background radiation reveal that the Milky Way is moving at a speed of 600 kilometers per second. Part of this motion is directed toward the Great Attractor, and part of it is due to the impending collision between Andromeda and the Milky Way. According to scientists' calculations, the spectacular encounter of these two galaxies will occur exactly 4 billion years from now. If our descendants are still alive then, they will witness this magnificent meeting up close, but it will likely be the last thing they see. Our position within the Laniakea supercluster determines the direction of this motion. All these movements are not random. The complex interplay between gravity, dark matter, and dark energy governs the motion of every object in the universe. While the Great Attractor pulls the Milky Way and thousands of neighboring galaxies towards itself, dark energy pushes distant structures away from us. Tonight, if you lift your gaze to the sky, as you watch the stars above, you realize that you are not merely observing the sky and the stars, you are traveling together with them in the same cosmic ship. This cosmic motion is not just a physical phenomenon, it is a process that dances with time itself. When we sum up all these movements, the distance a human travels in a lifetime reaches astronomical proportions. Earth's rotation, 1 billion kilometers. Orbit around the Sun, 80 billion kilometers. Motion within the galaxy, trillions of kilometers. So even if you have never left your own country, by the time you die, the place you die will be far from the place you were born. Knowing this through science alone is truly astonishing. This incredible journey also affects scenarios for the end of the universe. The influence of the cosmological constant and dark energy on galaxies will determine our long-term motion. Billions of years from now, when the Andromeda-Milky Way collision is complete, our combined galaxy will occupy a new location elsewhere in the universe. When we compare speeds on Earth to cosmic motion, the shift in perspective is astonishing. The fastest passenger plane flies at 900 kilometers per hour, yet you are already moving at 1,000 kilometers per hour simply due to the Earth's rotation. So if you have not boarded a plane, here is some good news. Even while watching this, you are moving faster than any aircraft. Fortunately, we cannot feel it. Formula One cars can reach speeds of 350 kilometers per hour,
Yet the Earth's motion around the Sun is 300 times faster. Motion between galaxy clusters is on an even greater scale. Our movement toward the Great Attractor is more than 300 times the speed of sound. The existence of dark matter is not merely a theoretical assumption. Vera Rubin's pioneering work revealed anomalies in galaxy rotation curves. While stars in the outer regions of galaxies were expected to rotate more slowly than those in the inner regions, they were observed to rotate at nearly the same speed. This observation did not indicate that the theory of gravity was wrong, but pointed to the presence of unseen mass in the galaxy. Yet we still do not fully understand what dark matter actually is. This is how one of the greatest mysteries in the history of cosmology emerged. Modern studies of galaxy clusters use gravitational lensing to map dark matter. The light from distant galaxies is bent by concentrations of dark matter, revealing the location of this invisible mass. To understand the future of the Milky Way, we must know our position within the galactic coordinate system. The Sun is located about 26,000 light-years from the galactic center, in the Orion spiral arm. This position is critical for calculating cosmic motion. Our location in the galactic plane also determines the cosmic radiation we are exposed to. You may wonder what this has to do with us, but even now, we are exposed to that cosmic radiation, and throughout thousands of years of evolution, all living beings have been exposed to it. How much this cosmic radiation may have influenced evolution and humans is an open question. Our distance from supernova explosions is considered one of the reasons for past mass extinctions. Over the 13.8 billion years since the Big Bang, the solar system has completed countless orbits within the galaxy. In each orbit, it has passed through different cosmic environments, encountering varying levels of radiation. The local bubble, where the solar system is located, is a typical example of intergalactic matter distribution. This bubble was created by supernova explosions approximately 10 to 15 million years ago. These explosions were so powerful that they ejected all surrounding matter and planets outward, forming a vast cosmic void. The matter density inside the bubble is 10 times lower than the average galactic density. This affects the amount of cosmic radiation reaching Earth. Cosmology researchers study how such environmental changes impact climate and life. The boundaries of the local bubble are surrounded by hydrogen walls. Over the next millions of years, the solar system will approach these boundaries and enter a denser galactic environment. Dark matter forms a massive halo around the Milky Way. This halo is 10 times larger than the visible part of the galaxy and contains 90% of the total mass.
Particles in the galactic halo of dark matter have not yet been directly detected. However, their gravitational effects maintain the rotational structure of the galaxy. The dark matter around us is everywhere, and we are gently floating within it, much like entering a vast cosmic ocean. On the scale of the Laniakea supercluster, dark matter filaments connect galaxy clusters. This enormous structure is the source of the gravitational pull of the Great Attractor. Due to the expansion of the universe and the influence of cosmic energy, our future motion will differ from what we experience today. The cosmological constant will slow down long-term galactic motion and eventually halt it. Billions of years from now, in end-of-universe scenarios, individual galaxies will drift apart due to cosmic expansion. If we were alive at that time, looking at the sky, we would likely see no stars around us. Measurements of the cosmic microwave background radiation provide data supporting these scenarios. The current age and expansion rate of the universe indicate the cosmic isolation that awaits us in the distant future. From a cosmological perspective, there is no such thing as stillness. Every moment, every second, we are part of a cosmic journey that will continue from the Big Bang to the end of the universe. And you are one of the most mysterious participants in this incredible journey.
The next time you look up at the night sky, try to find the Andromeda Galaxy. Go somewhere far from city lights, completely free from light pollution, and attempt to spot this cosmic giant somewhere out there. Currently, it appears as a faint blur in the distance, but 4.5 billion years from now, this collision candidate will dominate our sky. The collision between Andromeda and the Milky Way will be the most dramatic event in our cosmic history and will completely reshape the future of our galaxy. In the 1920s, Edwin Hubble's groundbreaking discovery revealed that Andromeda is a separate galaxy located 2.5 million light-years away. Light, the fastest thing we know in the universe, still needs 2.5 million years to travel this distance. Thinking about this helps us grasp the scale of cosmic distances. Measuring the distance was relatively easy compared to determining the direction of motion. A critical moment in cosmology came in 1957 with Dutch astronomer Hendrik van der Hulst's work. Using the 21-centimeter hydrogen line, he measured Andromeda's radial velocity, minus 296 kilometers per second. This negative sign indicated that the galaxy was not moving away from us, but rather approaching. Until 2012, astronomers could not be completely certain. Lateral motion components are crucial for measuring motions between galaxy clusters. Precise measurements from the Hubble Space Telescope, led by Song-Mo Tony Son and his team, finally confirmed that a collision between Andromeda and the Milky Way is inevitable. The term galaxy collision can be misleading because this process is not an instantaneous crash. It is a complex dance lasting hundreds of millions of years. What does it mean for two galaxies to collide? Will planets, stars, and all the dark matter surrounding us collide with the material in the other galaxy? The surprising truth is that stars almost never collide. Most of a galaxy's volume is empty space. Gravitational interactions are the true architects of the collision. As the two galaxies approach, tidal forces come into play. The same physics that creates ocean tides on Earth operates on a galactic scale. Parts of the galaxies closer together experience stronger pull, while distant regions feel weaker attraction. This tidal stress can tear apart spiral arms and form tidal tails. Much like the arms of an octopus, these galactic extensions can stretch tens of thousands of light years and become sites of intense star formation. As the universe continues to expand, the distance between Andromeda and us will keep decreasing. The first gravitational effects will be felt in about 2 billion years, during which the structures of both galaxies will start to change. In the cosmic microwave background reference frame, both galaxies are moving toward a common center of mass. This motion is not just a straight-line approach, but a complex orbital dance. This enormous cosmic waltz will directly affect the lives of billions of planets and stars, including our own. Before the main collision, the halos of both galaxies will begin to interact. The merging of dark matter halos will start long before the visible matter does. This phase is a critical turning point for the future of the Milky Way. The main merger process, beginning 4.5 to 5 billion years from now, will occur in multiple passes. The first pass will last over 100 million years, during which the galaxies will move apart again, Gravitational bonds will then pull them back together.
Each subsequent pass will take less time than the previous one. Energy will concentrate, motions will accelerate, and the dance will become an energetic, thrilling waltz. During this period, gas clouds will compress, triggering intense star formation bursts. During the galaxy collision, the star formation rate may increase 1,000-fold. This era, known as the starburst phase, will see millions of new stars born in brilliant blue-white light, illuminating the galaxy in spectacular fashion. Even if stars do not collide directly, cosmic motion will dramatically change their orbits. The regular spiral structure will transform into complex elliptical orbits. Do you think in this great cosmic waltz, the solar system or even humanity will manage to survive? Will we collide with another star and die instantly? Or will we be flung to some corner of space? Or will we freeze to death because we move away from the sun? Which of these do you think is more likely? Statistically, the chance of the solar system remaining intact is quite high. Interstellar distances are so vast that close encounters will be rare. However, some stars will be completely ejected from the galaxy, sent into cosmic exile. The gravitational dynamics that have been operating since the Big Bang will reach their peak during this process. The Sun's regular orbit around the galactic center will end, replaced by chaotic motion. The supermassive black hole at the center of each galaxy will play a critical role during the collision process. Sagittarius A at the center of the Milky Way, 4 million solar masses, and Andromeda's central black hole, 100 million solar masses, will eventually merge. This merger will be the most powerful source of gravitational waves in the history of cosmology. A great vibration will spread throughout the cosmic waltz, and this vibration will be felt across the universe. The gravitational waves predicted by Albert Einstein will reach their peak during this process. The merging black hole can swallow nearby stars or eject them from the galaxy. At the same time, it can produce intense energy jets, which will affect the galaxy's evolution. When the merger process is complete, the resulting new galaxy will have completely changed the future of the Milky Way. Astronomers call this merged galaxy Milky Way. The Milky Way we live in will no longer exist in the universe. A completely new entity will have been born, possibly containing entirely new forms of life. Milky Way will be a massive elliptical galaxy. Spiral arms will disappear, replaced by a more irregular but large structure. The galaxy's total mass will be slightly less than the sum of the two galaxies because some matter will be scattered into space during the merger.
The merger of dark matter halos will determine the galaxy's final shape. This process will show similar characteristics to other mergers within the Laniakea supercluster. Intense star formation during the merger will rapidly deplete the galaxy's gas reserves. Each new star formation will appear like a fireworks display in the universe. But this intense fireworks show will also mark the beginning of galactic death. After this burst, which will last only 100 million years, new star formation will almost come to a halt. Only long-lived red dwarf stars will remain. These small, dim stars can burn for trillions of years. In end-of-the-universe scenarios, red dwarfs will be the last living stars. Large, bright blue stars will finish their lives quickly. Sun-like stars will become white dwarfs. The galaxy will gradually grow dark. Dark energy and the cosmological constant will determine the galaxy's fate in the post-merger period. As the expansion of the universe accelerates, Milky Way will increasingly move away from other galaxies. Just as cosmic expansion pushes everything apart, it will also push the newly born Milky Way galaxy toward a lonely corner of the universe. If we can truly survive, then in the sky, we will see only the stars belonging to our own galaxy. Billions of years from now, we will see only the stars of our own galaxy in the sky. This process will also affect our connection with the Great Attractor. When the effect of dark energy surpasses gravitational attraction, cosmic structures will drift apart. Astronomers can observe similar galaxy collision examples in different parts of the universe. The Mice galaxies, 290 million light-years away, show the early stages of a merger. Their long tidal tails reveal the initial effects of the collision. ARP 220, 250 million light-years away, is a pair captured in the middle stages of merging. A galaxy 100 times brighter than the Milky Way we live in. Who knows how many billions of times more stars it contains compared to ours? Can you imagine? Observations by the James Webb Space Telescope in 2023 showed that intense star formation has now ceased. These examples provide clues about how the Andromeda and Milky Way collision will unfold. Each merger is unique, but the fundamental physical processes are the same. From a cosmological perspective, galaxy mergers are part of the normal evolutionary process of the universe. Since the Big Bang, billions of mergers have occurred, and the future of the Milky Way will be a continuation of this cosmic tradition.
Have you ever thought that the equations developed by an 18th century French mathematical genius for optimizing shipping are now used to predict the past and future of galaxies? Equations originally created to solve Napoleon's logistics problems are now used to explore our cosmic neighbors? The mathematics developed by Gaspard Monk during the Revolutionary era has become the most powerful crystal ball in the history of cosmology. In 1792, Gaspard Monk, serving as France's Minister of the Navy, was working on optimizing the transportation of materials on ships. The equations he developed were later expanded by André-Marie Ampère and began to be used in economic resource distribution problems. Who could have predicted it? The studies made to optimize trade routes revealed the secrets of the mysterious paths to the universe. During World War II, Soviet mathematician Leonid Kontorovich applied the Monge-Ampère equations to military logistics problems. However, the real breakthrough occurred in the 1970s thanks to Jim Peebles, working at Princeton University. Even though the Big Bang theory had been accepted, in the 1960s, cosmology was not considered a serious scientific field. Very little observational data was available, and most astronomers thought the field had no future. However, Peebles persisted and developed almost all of the foundational building blocks of modern physical cosmology. In the 1970s, French astronomer Roger May and Russian scientist Andrei Kofoid, following Peebles' work, fully adapted the Monge-Kontorovich equations to cosmology. How could these seemingly ordinary procedures help us understand the universe? Although technically simple, it was a revolutionary approach, taking the current positions of galaxies and using the laws of gravity to calculate where they had been in the past. Since the expansion of the universe and gravitational interactions between galaxies are known, this calculation was theoretically possible. Brent Tully and his team used this method to create the Cosmic Flows catalogs. Each catalog contains the positions and velocities of tens of thousands of galaxies, forming enormous datasets. When these massive datasets are combined, they reveal the paths that galaxies have traveled for billions of years and allow us to successfully map them. The accuracy of cosmic motion predictions decreases as we go farther back in time. Each step increases uncertainties. The farther we go from the present, the harder it becomes for us to predict. Technically, it cannot go all the way back to the Big Bang, but predictions spanning several billion years are fairly reliable. Despite these limits, the method can provide precise forecasts about the future of the Milky Way and the collision of Andromeda and the Milky Way. The future positions of galaxy clusters, the trajectory of our movement toward the Great Attractor, and the evolution of our location within the Laniakea supercluster can be calculated.
Tully and his team's continuously updated catalogs have become one of the fundamental resources for cosmology research. Each new observation increases the accuracy of predictions and refines the parameters of the universe's expansion. The greatest success of the Monge-Kentorovich method is that it revealed the true nature and scale of the Great Attractor. This cosmic phenomenon, a mystery for decades, began to take shape thanks to the mathematical crystal ball. This giant, hidden in the danger zone, had finally begun to take a form that we could understand. Galaxy motion maps, combined with measurements of the cosmic microwave background radiation, confirmed that the Norma cluster is at the center of the Great Attractor. The Norma cluster, 220 million light-years away, is several times larger than a typical galaxy cluster. But more importantly, it is located at the gravitational center of the Laniakea supercluster. This is the common gravitational point of 100,000 galaxies. Mapping the distribution of dark matter is not possible with traditional observational methods. However, cosmic motion analyses indirectly reveal the locations of the unseen mass. It was as if we were meticulously following the traces left behind by a criminal. The cosmic motions of galaxies are guided by the concentrations of dark matter around them. By analyzing this interaction, three-dimensional maps of dark matter filaments can be created. The distribution of dark matter within the Laniakea supercluster explains why the supercluster's four main branches are organized in this way. Each of the Virgo, Hydra Centaurus, Pavo Indus, and southern branches was shaped along dark matter filaments. The greatest power of the Monge-Kentorovich method is its ability to look both backward and forward. That is, we could determine both the birth and death times of galaxies using only this method. This two-way analysis provides unique opportunities to test cosmology theories. Backward-looking analyses confirm theories of galaxy formation. They show how the mass distribution after the Big Bang evolved into the complex structures we observe today. This process covers periods before dark energy had yet to dominate. Forward-looking projections shaped scenarios for the end of the universe. Under the influence of the cosmological constant, they predict which structures will survive and which will disperse. The Laniakea supercluster is not alone. Monge-Kentorovich analyses reveal the motions of neighboring superclusters as well. The gravitational influence of the Shapley supercluster is felt on even larger scales than the Great Attractor. The Shapley supercluster, 650 million light-years away, is even larger than the Laniakea supercluster. It is such a massive supercluster that it can exert influence over everything around it. Our movement toward the Norma cluster is, in fact, also part of Shapley's distant influence. This multi-layered system of motion illustrates the hierarchical structure of the universe. Galaxy groups, groups of groups, clusters, superclusters, and superclusters influence even larger structures.
In 2008, NASA astronomer Alexander Keshlinsky discovered a strange signal in the cosmic microwave background radiation. Analysis of the kinematic Sunyaev-Zeldovich effect showed that galaxy clusters exhibited a large-scale flow in the direction of Centaurus Vela. This dark flow was moving at 600 to 1,000 kilometers per second and spanned a significant portion of the universe. This mysterious flow was so enormous that we had never seen anything like it before, and scientists struggled to explain it. The problem was this: known density variations in the universe were insufficient for such large-scale coherent motion. In 2013, ESA's Planck satellite announced that it had found no evidence for dark flow. However, the debate continues. If it is real, the theories of the universe's expansion and dark energy may need to be reconsidered. Cosmic flows are not shaped solely by gravity. Sound waves left over from the Big Bang also play a role.
When the universe was a few 100,000 years old, sound waves propagated through the hot plasma. These ancient sound waves are likely still spreading into the universe's distant corners. When the cosmic microwave background radiation was released, these sound waves froze. These structures, called baryon acoustic oscillations, or BAO, can be observed today in the distribution of galaxies. In 2023, Brent Tully, Colin Howlett, and Daniel Pomerade discovered that nearby clusters are arranged in a shell with a diameter of 400 million light-years. This structure may be a remnant of a single baryon acoustic oscillation. Centered on the Buttes supercluster, this structure was named Ku'olana, from Hawaiian creation hymn Murmurs Awakening from Deep Darkness. The increasing influence of dark energy will dramatically alter future cosmic flows. Monge-Cantor-Revis analyses can predict the timing and scale of this change. These cosmic flows, ongoing for billions of years, will eventually begin to reverse when the time comes. The dominance of dark energy, which began 5 billion years ago, is gradually weakening gravitational pull. Structures on the supercluster scale will no longer merge, and existing ones will disperse. In end-of-universe scenarios, only structures held together by strong gravitational bonds will survive. The Laniakea supercluster will disintegrate, and our journey toward the Great Attractor will be cut short. However, the collision between Andromeda and the Milky Way will still occur because this process began before dark energy dominance. Although powerful, the Monge-Cantor-Revis method is not perfect. Galaxy mergers, supernova explosions, and changes in dark energy can create unpredictable effects. Understanding the entire universe remains extremely difficult, and it can present us with surprises at moments we least expect, sometimes beyond what our current mathematical knowledge can explain. The greatest uncertainty comes from the nature of dark energy. If the cosmological constant behaves differently than assumed, all future predictions could change. Therefore, cosmology researchers must constantly update their forecasts with new observations. Still, this mathematical crystal ball provides unique insights into the Milky Way's future and the expansion of the universe. The 18th century mathematician's problem in navigation illuminates universal destinies in the 21st century.
To understand the large-scale structure of the universe, imagine building a massive Lego tower. Each piece is carefully placed on top of the other, and over time, an incredibly complex architecture emerges. However, every piece of this giant Lego tower is alive and flows in perfect harmony within itself. This is exactly how the structure of our universe is, organized in a hierarchical order, with each level larger and more complex than the previous one. One of the most fascinating aspects of cosmology is discovering this perfect order of the universe. Over billions of years, thanks to gravitational forces, matter clusters, galaxies form, and larger structures are built. This process is a story that has continued since the Big Bang, patient, persistent, and never-ending. The smallest structures of the universe, galaxy groups, are the first examples of cosmic families. Our Milky Way galaxy, along with Andromeda, Triangulum, and about 80 small dwarf galaxies, forms a family called the Local Group. Even as you are reading this, the members of this galaxy family are moving toward each other in cosmic motion. Of course, while you are listening silently, massive galaxies trillions of times larger than our head are moving toward each other in cosmic motion. The Local Group has a diameter of about 10 million light-years, a distance difficult for the human mind to grasp. To understand this distance, consider that light travels 300,000 kilometers per second, and it takes 10 million years for this beam of light to reach from one side of the group to the other.
Compared to galaxy clusters, this is small, but having trillions of stars together is truly incredible. The formation of these groups is not random. The invisible networks of dark matter act as glue that holds galaxies together. Dark matter is 6 times more abundant than normal matter, yet it cannot be seen. We can only understand its existence through gravitational effects. So what is this white web that surrounds us and our entire galaxy? Have you ever thought about it? If galaxy groups are like a village, galaxy clusters are the great metropolises of the cosmos. Our nearest neighbor, the Virgo cluster, contains more than 2,000 galaxies and spans 100 million light-years. The mass of this enormous structure is 10 to the 15th times that of the Sun. That is a 1 followed by 15 zeros. The Virgo cluster, at the heart of the Laniakea supercluster, is not only large but extremely active. The giant elliptical galaxy M87 at the center of the cluster contains a supermassive black hole with 6.5 billion solar masses. This black hole is so powerful that it shoots plasma jets 5,000 light-years long, as if throwing fiery spears into the universe. It's as if a cosmic dragon is hidden in our universe, and every time it gets angry, it breathes fire.
The gravitational force of the Virgo cluster is so strong that it even affects our local group, which is 65 million light-years away. Right now, all neighboring galaxies, including the Milky Way and Andromeda, are being pulled toward this massive cluster. This movement occurs at hundreds of kilometers per second, but the distances are so vast that our arrival will take billions of years. One of the greatest discoveries in the history of cosmology was the realization of the existence of superclusters, the structure that Gerard de Vaucouleurs called the local supergalaxy in the 1950s turned out, over time, to be just a small part of a much larger system. In 2014, the groundbreaking work of Brent Tully and his team revealed the true size of the supercluster we belong to. Laniakea, a name meaning immense heaven in Hawaiian, is a massive structure containing 100,000 galaxies and stretching 520 million light-years. To grasp this scale, consider this. Even if you traveled at the speed of light, it would take 500 million years to go from one end of Laniakea to the other. The most fascinating feature of Laniakea is the discovery that all galaxies within it flow toward a common center. This center, the Great Attractor, located near the Norma cluster, is a mysterious region pulling 100,000 galaxies toward itself with invisible gravitational forces. As far as we know, there are 100,000 galaxies, and this invisible network dominates all of them and maintains them in great harmony. Can you comprehend the size of this massive white network, which we would call giant, yet even that term would be insufficient? In the process of the universe's expansion, matter did not spread randomly. Instead, an immense network emerged through the interaction of dark energy and dark matter. This cosmic web consists of filaments, walls, and enormous voids. Superclusters are located at the nodes of this web. Between them stretch almost empty regions, millions of light-years long, cosmic voids. These voids are not completely empty. They are filled with dark energy and act as the engine of the universe's accelerating expansion. Astronomers analyzing cosmic microwave background data discovered that the foundations of this web structure were laid just 380,000 years after the Big Bang, when the universe was much hotter and denser. At that time, structures with small density fluctuations grew over billions of years to form the enormous superclusters we see today. The hierarchical structure of the universe is not static. It is constantly changing and evolving. Galaxy collision events occur at every level. Small galaxies merge into larger ones, groups become clusters, and clusters become part of superclusters.
The most dramatic example of this process is the collision of Andromeda and the Milky Way. This event, which will occur 4.5 billion years from now, will result in the local group becoming a single giant galaxy. But this is just the beginning. Within approximately 100 billion years, all members of the local group will merge into a single mega-galaxy. Can you truly grasp what 100 billion years means? To make it easier to understand, I am honored to inform you that 100 billion years is more than 7 times the entire history of the universe so far. Indeed, it feels like infinity to us.
Dark energy, also known as the cosmological constant, threatens the future of the universe's hierarchical structure. 5 billion years ago, dark energy surpassed matter in the total content of the universe and has been increasing its dominance ever since. The effect of dark energy is destructive on large structures that are not yet fully gravitationally bound. Loosely bound systems, like superclusters, are doomed to disperse due to the accelerating expansion of the universe. Only structures with very strong gravitational bonds, galaxy clusters and groups, will remain intact in the future. This situation is both hopeful and melancholy for the future of the Milky Way. The local group will maintain its strong bonds and continue to exist as a single megagalaxy. However, our journey toward the Virgo cluster can never be completed. Dark energy will increasingly pull us away. It is as if our great journey, lasting billions of years, will be left unfinished, bidding us farewell. Understanding this hierarchical structure allows us not only to comprehend the past of our universe, but also to understand how its end will unfold. Each level tells its own story, and together they form the grand symphony of the cosmos. Although the discovery of the Great Attractor was a revolutionary development in cosmology, scientists soon realized that it was only the beginning of the story. That is, we have only recently understood the portion of this mountain visible on the surface. What then are the mysterious and fascinating discoveries beneath this iceberg? One can't help but wonder. While trying to explain the Milky Way galaxy's movement at 600 kilometers per second, researchers realized that the Great Attractor alone was insufficient to account for this immense cosmic motion. This discovery revealed that the universe is filled with even larger and more complex structures. The Norma cluster, the heart of the Great Attractor, was defined as the common destination for the 100,000 galaxies in the Laniakea supercluster. However, detailed observations showed that even this massive galaxy cluster was too small to explain the Milky Way's speed on its own. It was as if a larger, unexplained force was hidden behind the control of this universe. Even when included in dark matter calculations, the gravity of the Norma cluster could not fully account for the observed velocity of the Milky Way. This situation forced us to reshape our understanding of cosmic motion. Within the expansion of the universe, interactions between galaxy collisions and galaxy clusters were far more complex than previously thought. When researchers discovered that the Great Attractor itself was moving toward another force, the extent of this complexity became clearer. At a distance of 650 million light-years, beyond even the Norma cluster, a massive structure known as the Shapley supercluster was discovered. This was added to our greatest discoveries. First noticed in 1930 by Harlow Shapley at Harvard College Observatory as a distant, indistinct nebula, this structure was later understood to be a supercluster even larger than Laniakea. The enormous mass of the Shapley supercluster affects every galaxy, galaxy group, and galaxy cluster across hundreds of millions of light-years. This cosmological giant pulls all the large structures around it, including the Great Attractor, toward itself. If we allowed enough time in the universe and dark energy did not intervene, the entirety of Laniakea would eventually merge into a single massive object, which would then continue its journey toward a similar structure at the center of the Shapley supercluster. In 2008, NASA astronomer Alexander Kashlinsky made a surprising discovery while examining the cosmic microwave background.
Observing a subtle signal known as the kinetic Sunyaev-Zeldovich effect, he noticed that galaxy clusters exhibited a coherent flow in a direction between the Centaurus and Vela constellations. No one, including scientists, had expected this discovery. The scientific world was once again profoundly shaken. The phenomenon, called dark flow, had a velocity between 600 and 1,000 kilometers per second, even faster than our motion toward the Great Attractor. Even more astonishingly, this motion encompassed a significant portion of the clusters in the universe. However, the density differences in the universe were not large enough to explain such a large-scale coherent motion. Although ESA's Planck satellite found no evidence for dark flow in 2013, debates on the topic continue. Is this mysterious motion real, or is it the result of observational errors? Questions like these are still being investigated by scientists day and night. If it is real, it means that our universe contains structures far larger than we currently know. To understand the complex motions of the universe, we need to go back to just after the Big Bang. When the universe was only a few 100,000 years old, it was 1,000,000 times smaller than today, and all of its matter was in the form of a hot, dense plasma. Within this plasma, density waves moved back and forth, just like sound waves formed on the surface of a drum. These sound waves are called baryonic acoustic oscillations. As the universe expanded and cooled, the plasma turned into neutral gas, and the cosmic microwave background was released. At that moment, these acoustic oscillations froze and were fixed in the positions and states of the universe at that time. In 2023, Brent Tully, Colin Howlett, and Daniel Pomerade discovered that nearby clusters, walls, and other structures of the cosmic web are arranged in a shell-like pattern. This discovery reminded us once again how exciting it is to unravel the mysteries of the universe. The radius of this shell is more than 400 million light-years and includes massive structures such as the Sloan Great Wall, CFA Great Wall, and the Hercules Complex. They named the structure Huale'ilana, a word taken from the Hawaiian creation hymn, meaning whispers of awakening came from the deep darkness. It is believed to be an individual baryonic acoustic oscillation resonating from the plasma era of the universe to the present day. Movements in the universe are not determined solely by attractive forces. With this discovery, we had unintentionally opened the door to much bigger questions. Things got even more interesting at this point. There are also repulsive forces. Even when we gather all the known mass sources in the universe, it is still not enough to fully explain the motion of the Milky Way galaxy. On the exact opposite side of the Shapley supercluster is something we have yet to fully map or understand.
This structure, called the dipole repeller, is one of the enormous voids that dominate a large portion of the volume of the universe. We do not yet have a precise understanding of its shape, size, or dimensions. The only thing we know is that it seems to participate in the large-scale movements that define motion in the universe. It is important to understand that these large voids do not merely leave matter behind, they actively push the galaxies at their edges. Despite being voids, they are filled to the brim with dark energy. Dark energy, the mysterious force accelerating the expansion of the universe, concentrates in these voids and pushes galaxies away from each other. All these attractive and repulsive forces create a tremendous ongoing cosmic dance in our universe. The collision of Andromeda and the Milky Way is just a small part of this grand picture. It was such a grand waltz that we still find it difficult to fully comprehend. While the 100,000 galaxies in the Laniakea supercluster flow toward the Great Attractor, they are simultaneously under the pull of the Shapley supercluster. Voids like the dipole repeller create an effect in the opposite direction. This complex balance of forces determines the ultimate fate of the universe. As dark energy continues to strengthen, repulsive forces will overcome attractive forces. This means the cosmic clock will not rewind.
the cosmic web will unravel and we will never reach the Great Attractor. The Milky Way's cosmic journey represents one of the greatest mysteries of the universe. Every new discovery raises even bigger questions and shows how complex and magnificent our universe truly is. Einstein's biggest mistake, the cosmological constant, has become the key to explaining one of the greatest mysteries of our universe today. Once again, we see that there can be very beneficial things behind what we sometimes see as mistakes. Who would have thought that a mistake could solve the greatest secret of the universe? In 1998, the discovery of the accelerating expansion of the universe by astronomers revolutionized the field of cosmology and brought the concept of dark energy to the attention of the scientific world. This mysterious force determines not only the future of the universe, but also the fate of the Milky Way, galaxy collision processes, and ultimately the end of all cosmic structures. When Albert Einstein tried to apply the general theory of relativity to the entire universe in 1917, the mathematical equations naturally predicted a dynamic universe. This was a true turning point for the scientific world. However, the scientific understanding of that era accepted the universe as static and unchanging. Therefore, Einstein added a term to his equations called the cosmological constant, a force that would balance the universe's tendency to expand and keep it steady. However, just a few years later, Edwin Hubble's discovery of the universe's expansion showed that Einstein's concerns were unnecessary. Einstein wanted to remove the cosmological constant, and his close friends remembered that he described this term as his biggest mistake. Yet this mistake would become the key to solving one of the deepest secrets of the universe. When Soviet astrophysicist Yakov Zeldovich realized that the cosmological constant was actually equivalent to the vacuum energy of space-time, it became clear how correct Einstein's intuition had been. Dark energy and the cosmological constant emerged as different expressions of the same fundamental concept.
Two independent research teams observing supernovae made a discovery in 1998 that would profoundly shake the scientific world. While observing Type A supernovae in distant galaxies, they noticed that the expansion of the universe was accelerating rather than slowing down. This discovery deeply shocked us because it was as if we had learned that gravity was working in the opposite direction. This unexpected finding shook the foundations of cosmology while winning the 2011 Nobel Prize in Physics. The most likely explanation for the accelerating expansion of the universe was a type of energy inherent to space-time itself, dark energy. This mysterious force makes up 70% of the universe, and its influence is steadily increasing. This form of energy, present since the Big Bang, becomes more dominant as matter density decreases. What dark energy exactly is remains unknown, but we can clearly observe its effects. We are certain that something great governs this order, but we have not yet seen what it is. According to the most accepted theory, dark energy is related to the vacuum energy of space-time. Quantum mechanics states that even space that appears completely empty is teeming with fundamental particles, a sea of energy constantly oscillating between existence and non-existence. As the universe expands, more empty space is created, which means more dark energy. As normal matter and radiation dilute, dark energy becomes stronger. 5 billion years ago, a critical turning point occurred in the history of the universe. For the first time, the matter density fell below the dark energy density. Since that day, the situation has only worsened.
Today, dark energy constitutes approximately 70% of the universe. In the future, this ratio will rise to 90%, then 99%, and will continue to increase forever. Since this process has no limit, dark energy creates a self-feeding cycle. The voids in the universe are the regions where dark energy is most concentrated. In fact, learning that these voids we thought were completely empty are filled to the brim with energy was truly one of our greatest discoveries. Massive structures like the dipolar repeller are almost entirely devoid of matter. Only occasionally are there thin ionized gas filaments or small dwarf galaxies. Since these regions are almost completely pure voids, they are overflowing with dark energy. These voids begin to actively push the galaxies at their edges. The repulsive effect of dark energy shows itself most strongly in these regions. Over time, the voids grow, merge, and push galaxies away from each other faster. The gravitational force that holds galaxies together is in constant struggle with the force of dark energy trying to separate them. The strengthening of dark energy means the hierarchical structure of the universe begins to unravel. Massive structures like the Laniakea supercluster start to break apart under the influence of dark energy before they can become fully gravitationally bound. The entire universe had begun to be split into massive pieces by these dark forces. The formation of these superclusters took billions of years, but dark energy will never allow them to be completed. Structures with strong gravitational bonds, like galaxy clusters, will survive. The Virgo cluster will continue to host thousands of galaxies. The collision of Andromeda and the Milky Way will also occur because the gravitational bond between them is stronger than the separating force of dark energy. However, we will never reach the Great Attractor. The four arms of Laniakea will never unite. Our interaction with the Shapley supercluster will never be completed. The cosmic web has already begun to unravel. Billions of years from now, the Milky Way's journey toward the Great Attractor will slow, stop, and reverse. This will be something we have never experienced before. The galaxies in the local group will merge to form a massive megagalaxy, but this galaxy will gradually become isolated. Within hundreds of billions of years, distant galaxy clusters and galaxies will fade and disappear from our view. They will move beyond our cosmological horizon and seem as if they never existed. Our megagalaxy will become a lonely island drifting in the void.
However, motion will not end here either. Gravitational interactions within the galaxy will continue to scatter stars randomly. When a star escapes the galaxy's gravitational control, it will be captured by the accelerating expansion and carried away forever. One by one, star by star, our galaxy will shrink. Hundreds of trillions of years from now, every macroscopic object in the universe will be completely isolated from one another. For the first time in a true sense, we will be alone. We will drift alone in a dark void with no neighbors. They will be separated by expansion faster than the speed of light. Every galaxy, every star, every planet will remain on its own. When nothing remains in the outer universe, there will be no reference frame to measure motion. There will be nothing to compare to the Hubble flow. No source of pull or push. The rest of the universe, whatever exists, will finally come to stillness. This absolute end will be the only moment when the old astronomers who thought the universe was static will be right. But by then, there will be nothing left to measure. This entire grim picture may not be definite, because the universe is always full of surprises, and we only know the visible part of the iceberg. Since we do not fully understand the nature of dark energy, it is possible that it could change in the future. Perhaps dark energy will weaken over time or transform into other forms. The combination of quantum mechanics and general relativity may bring new perspectives. Multidimensional theories, string theory, or laws of physics we have not yet discovered could change the fate of the universe. For now, we continue to watch the Milky Way's tremendous cosmic journey and unravel the greatest mysteries of the universe. Every new discovery allows us to better understand our destiny and raises new questions.
Whatever the ultimate fate of the universe, this journey itself is a priceless adventure for humanity. These videos are really made with a lot of effort and go through many research processes. That is why your support is very valuable to me. Don't forget to like the video and subscribe. Thank you in advance. See you in the next video.